Good evening, everybody. I'm delighted to welcome you to the 2015 Peter Dormer Lecture. My name is Kat Rossi and I'm a design historian based at Kingston University and a member of the Peter Dormer Committee, chaired by Tanya Howard and Hans Stouffer, which organises this annual event. I don't want to spend too much time delaying us from tonight's main attraction, but I would like to spend a few minutes introducing the lecture series and this year's rather wonderful speaker. So for those of you who haven't been able to join us before, a few words on what lies behind this evening's event. The series is held in memory of Peter Dormer, the writer and critic, who was responsible for some of the 20th century's most seminal ideas about craft, expressed through his contributions to magazines such as Crafts, but also his authorship and editing of books such as The Art of the Maker, The Culture of Craft, and The New Jewellery with Ralph Turner, and his curation of exhibitions such as Beyond the Dovetail. I'm sure you'll agree, an active and important life until his untimely death in 1996. Speaking personally as somebody who researches, writes and teaches a new generation of designers and makers about craft, I, like many others, have found great worth in his ideas. From asserting craft's value amidst its marginalisation in industrial modernity, to the rich complexity of craft's relationship with art, design, technology and architecture, amongst other areas. The importance of both notions such as tacit knowledge, but also what Dormer called good quality writing and argument, in order to ensure that craft's value is well recognised. However difficult, as he also acknowledged, it can be to put what is valuable about craft into words. Now in its 17th year, the lecture series has had a rather stellar lineup of speakers. From last year's Daniel Charney, to previous voices including Martina Margetts, Grayson Perry, Jeremy Myerson, Tanya Howard, Charles Jenks and Edmund Duval, to name just a few. Joining this illustrious company this year is Cecil Balmond. In many ways he needs no introduction. Trained as an engineer, today Balmond is one of the world's leading structural designers, both in fact. In his 4 decades at Arup Associates and now at Balmond Studio, the research-led practice he set up in 2010, which now has offices in London, Sri Lanka, Singapore and the US, and amongst many other activities, Balmond has engendered and enabled some of the most significant structural feats of the 20th and 21st centuries, both independently and in collaboration with architects including James Stirling, Rem Koolhaas and Toyo Ito, and also artists such as Anish Kapoor, as part of its extension more recently into the art world. But it isn't just Balmond's well-deserved reputation as a polymathic powerhouse of engineering creativity, including his mastery of digital technologies, which led to the invitation to deliver this year's lecture. So I would like to take the liberty of suggesting that there are also a few significant affinities with Balmond's practice and Dormer's ideas, and with the condition of craft more generally today. Perhaps most significantly, for those who are uncertain about what kinship there could be between a master of algorithms and a champion of the handmade, is their approach to technology. Like many who support craft traditions, Dormer was no Luddite. As he wrote in 97's The Culture of Craft, computer technology presented craft with what he called its most serious philosophical and practical challenges. Yet Dormer also recognised that new technologies presented new possibilities for craft, and that such technologies would not obviate the need for what he called hands-on making or personal know-how. Similarly, in interviews, Balmond has described the importance of what he terms intuition in how to make use of technologies throughout the design and making process. Furthermore, it seems that his passion for technology is not based on some teleological interest in technological progress to achieve the superlatives of the biggest, the highest, the tallest. Rather, Balmond has discussed the importance of introducing human qualities into the design, and feelings and experience into the function and effect of a building or structure. Values an audience of craft fans I'm sure can all appreciate. And I'll come to an end by briefly suggesting 3 other potential affinities between Balmond and craft, and I'll be interested to hear what you and also the rest of the audience think of these. First, like craft, Balmond refuses to be easily defined or is difficult to define, in his case by adopting the boundary-crossing mantle of artist, architect and engineer. Second, like craft, Balmond has long played a fundamental but perhaps supplemental role in contemporary culture, slipping into the background as credit has been given elsewhere. But, fortunately, like Craft too, in recent years he has started to enter the limelight and get the attention he deserves. And last but not least, like Craft, Balmond places a huge emphasis on materials, on respecting materials and qualities of materials, and also those who engage with them. The images that I chose for this short introduction come from Balmond Studio's website, and I've kind of read how Balmond has described his collaborative process or his collaborative relationship with fabricators, respecting their technical and material knowledge and what the qualities of such materials and knowledge can bring to the design process. Fittingly, it is materials that Balmond will discuss this evening. As we can read in the introduction, the description, these include wood, ceramics, glass, brick, concrete and steel, but also, befitting his position at the vanguard of digital technologies, numbers and algorithms. So I can think of no better speaker for this year, and so I would now like to invite Cecil Balmond to the stage to present the 2015 Peter Dormer Lecture, and thank him in advance for what I know will be a fascinating talk.
Thank you, Kat, and good evening. Well, when I was invited to give this talk, obviously I thought of Peter Dormer, and I read some of his writings on ceramic, pottery, and the mind goes to material and craft, of course, and that's been always a funny word between people who chase fine art and look down on craft. I've never seen a distinction. I just do, make, design, use materials, use tools. And thinking of material, of course, in our building design we use brick, concrete, steel, glass, and standard templates of geometry like rectangle, square, circle, and in modern, with computer technology now, some parametrics and curvilinear forms. And I've done the same for 40 years of my practice, both in Arab and also in my own practice. But about, 20 years ago probably, as long as that, I started playing with numbers. And literally it was playing with numbers. It was moving some things around, and I found that geometry was affected quite significantly. And this was with numbers not being a cipher, but having potential to do things. They had magnitude, they had vectorial attributes. And so it was a short step from that to actually starting to consider numbers as material. And it was provocative thought and speculative, highly speculative. But I started chasing that. So it's not all my work that deals with numbers, but I thought in naming this talk Material Number and taking a chance to show you some of my recent research in honor of this occasion as well, for the first time in public, to share some of the recent research where actually numbers are material. It leads to objects, it leads to artistic endeavor, it's all part of craft as well. And if Peter Dormer was here, I would wish he probably would enjoy seeing this kind of attitude to numbers as a new kind of material. So when we make things, we have the material and we have tools. And in this case, our hand, or we have implements. And to some extent, the products we make are influenced by the instruments we use. There is a kind of a feedback. We also have molds as templates, and then there's the simple characteristic of building through unit ideas of modularity, but equally with ingenuity and design, we can overcome the prescription of the module. We also have templates. So primitive looms with more complex eyeing and more complex loom, you get different patterns. And we have stencil making, another kind of template to design with. In architecture, we use proportion and grid. And underlying the idea of proportion is really a more active concept called ratio. And somewhere along the years, the idea of this distance to that distance being an ideal rectangle led to an idea of a perfect rectangle, or something called the golden rectangle, which led to the much celebrated and talked about golden ratio. And that's to do with numbers like if this was 5, that is 8. If that's 8, that is 13, and so on. And this had a boost, this kind of proportion theory, ratio theory, in nature, when people found as you track the spiral of a plant growing and the leaves trying to track the light without the next one overshadowing it as it keeps spiraling up, numbers, if you track the first growth, which is here, and as you go around, you find on the third spiral the 8th growth, and the adjacency of numbers like this, 3 and 8, 5 and 8, and as you go on, 13 and 8. This started echoing some of the perfect ratios of the golden ratio. And so when we study the sunflower and start tracking its growth from the first seed outwards, so here's the first one, second, third, fourth. It starts growing in sort of triangles like that, spinning round, trying to capture the light as a maximum. And surprisingly, certain adjacent numbers, as it grows, are spaced 13 apart, 8 apart, and these were numbers again cropping up in what's known as the Fibonacci numbers, leading to the golden spiral, golden section. And this is a simple feedback loop where to get the next number, you go backwards 1 and go forward 1. 5 and 3 make 8, 8 and 5 make 13, and so on. It looks like nature just doesn't grow spontaneously without some kind of break in the system. You go back 1, you go forward 2. And it leads to this kind of spiraling form, the logarithmic spiral. So here we have a set of numbers that negotiate between geometry and algebra. So the three big bastions of our mathematics is algebra, the continuum of fluid nature, geometry of a fixed shape nature, and numbers. And for me, they negotiate between the two. So the fixed ratios that come out of the numbers also lead to an implied algebra of the logarithmic spiral. And here you can see it more clearly. Perhaps this was a tiling pattern that I devised for the V&A that never got built, the building in Knightsbridge. But if you start with 1 pixel square, and then you take a 2 pixel square, and a 3 square, and a 4, and you go on and you track this, you start getting these numbers again, which leads to the golden ratio, the logarithmic spiral. So there's a definite bridge which intrigued me between fixed geometries and fluid shape. And the negotiating power between them was numbers. So I started exploring more, and the very first exploration I did began with a simple grid like this many years ago, where I took a simple sine curve. So I took the top as +1, the bottom as -1, and the middle as 0. And just shunting a curve like that up and down on a grid, as I said, it was like playing, I wasn't sure what I was doing. I just shunted the numbers along, which meant the sine curves were just moving up and down in a template. Freeze frame it, and then I gave it actual dimension of 4.5 meters for the grid and 1.5 meter for the amplitude of the wave. I had no idea what would come out, but this did. A lovely curving, doubly curved surface. And the reason I did this was I was commissioned by Álvaro Siza, the Portuguese architect, to design the roof for, I think it was Pavilion of the Oceans, and he wanted a sort of metaphor of the waves for the roof. And so this was the application of those sine waves, and that was the building I applied it on. And so here we've got, and you can see that I really couldn't have second-guessed these kind of waves. If I tried to draw it out, you cannot really conceive this in 3D without this simple little engine I had, like a little algorithm, most primitive of all, +1, 0, -1, shunting up and down. Join them up, you get this curved topology, and that shape then was applied to a space frame to support it. And that was it in Coimbra, in Portugal. Very simple, very primitive application of the numbers, very basic, but quite a good effect in the curving roof form. As I said, I could not have second-guessed it. It just came out of that grid shunting. The sides of the building are in cork, which is nice. And the inside also has the undulations, but against the fixed geometry of the sides. So the fixed box container with this fluid form. Looking back on it, probably we should have spent more time with the sides, just putting a different kind of curvilinear form on a Cartesian form has some problems too at the junctions. This idea of the fixed form, though, is a very old idea, and the idea of ratio has been there for a long time, and these are typical ratios Palladio used in ideal room formations. And this is a table that was used extensively in the Renaissance and it was done earlier by Nicomachus. And it's a simple tripling of numbers this way, doubling of numbers this way. And in there, in this area particularly, you get most of the proportion of most of the rooms built. Now, that is, and the idea here of ratio is really one of subdivision. If you look at all this 2 by 3, 3 by 5, it takes the boundary as a given. There's no concept of going past a boundary. You're within the boundary and you start subdividing. That is essentially the classical legacy we have received. A fixed boundary, it comes from the idea of a fixed source, the one God. Everything emanates from a principal origin. Given that, there are boundaries around. So what is different is instead of reducing the form, if you start to compile the form. And so here was an idea. If you start with half and go to a third, you can't keep going, reducing any. You're compiling the form. You've got to go out of the original boundary to keep going. And then you do that, which gives you the white lines. Then as an architectural motif, I extended all these lines, and you get something like that. If you make this all in steel plate, cut the corners out, 4 corners, and you fold it, then you get the Serpentine Pavilion, the well-known and well-celebrated now pavilion, which I did with Toyo Ito. And in here, then the architectural effects and the design of effects come on. There's always an algorithm. There's a kind of translation area where you're beginning to turn it to design, and then the translation into materials, which then is your final design. And in here, the network is obvious, but we coffered the slab, the roof. So you get this in and out, precipitation almost, and it opens up the vertical dimension. And of course, there are no corners as such defined. The oblique lines, when you fold, take your eye round the corner. You've got to zip around. You don't have a corner definition. And that's fundamental to have a sense of release and no confinement. And this is only 17 meters square. But surprisingly, when you're in it, or when you were in it, you never felt confined. So, and if you look, the whole thing is a network. In there, some of the lines are stronger, but they all are one massive structural network, feeding off each other. There is no definitiveness of one line or an obvious structure. It's the entire net. And then also, to help with the idea of speed, we set back the panels so you can see the lines shooting past. Here's a thicker line for structural reasons. Here's another one, but as I said, the entire thing holds itself together. And you get these kind of effects. The corner has been undermined, and you get this sculptural feeling of this object, and it even doesn't bottom out. So the corner is completely undermined even at its root. And you get these moments of great transparency and opacity, all in the same network of lines. Now, if you take that ratio that actually governed this, and it's a compilation, not a subdivision, because it's something is alive when you do things. When you compile, you're sensitive to your start point. So if they shifted, instead of half to a third, if it went quarter to a quarter, you get something very, very different, a kind of vortex. And now if you cut the corners out and folded this, then each side would have a pattern like this, moving up, and over the roof you'd get this vortex spinning. So very sensitive to start points, not the simple reduction. And if you had a six-sided object and went back to the original ratio of half to a third, then you get something like this, interconnecting, but gradually the center opening up. And as I increase the sides to 20, I can braid a ring. Same idea, half to a third, just different geometry templates, and the compilations giving you different typology. And here, if I chose silver thread, it could be a bangle, or just in Indian culture, it could be just string making a Brahmin bracelet. Or if this was 1 kilometer wide in space, it would be massive steel box girders interconnecting, and you walk through into all your chambers. So pattern is scaleless, and the function defines the material, slightly different to a normal process where you may think of a material and think of a function. Not strictly true all the time, but generally these kind of scaleless ideas, pattern making in a way, leads to functions that then define the material, and structure and configuration fall out. Quite the reverse to a normal way where we think of a shape and a structure first. If I zoom out of that way up, this is 500 meters up looking down at the pavilion. The pavilion's that little black dot. Then you see fundamentally the organizational system of this spiral. The half to a third that had to keep going out and breaking its boundaries actually is a spiral form. And if you zoom back in, right into that little area there, you get back into what might appear a chaos of intersection, but the alternating, and nowhere does this repeat. And this was one of the first examples of no drawing work that I ever did. It went straight from my computer to the cutting machines. So it was entirely in one way crafted, because the design was algorithmic. The actual design was that concept of a half to a third in abstract terms, and then somewhere you lose that control till it emerges again in material, and then choosing the wells and choosing how you make connections then puts in certain artistic effect. I love this slide because it shows the subdivision of a neoclassical form, strictly subrhythms, to something that cannot be contained. And the corner here again disappears. And the contemporary, with its own internal logic, can sit well alongside classical logic. Both are valid forms, and one doesn't deny the other. So we have the pavilion, and for me it's a kind of active meditation on geometry, some kind of animate sense of things being made. And as Japanese architect Isozaki said when I took him here and he visited, he said, Cecil, for the first time I've seen something that is architecture and structure and ornament all in one. And I hadn't thought about it that way. But it was true. I started seeing ornament everywhere I looked, and everywhere I looked was structure, and it was an object of art or architecture, whichever way you want to call it. Nice graphic, zooming out and putting the spiral in a tiling form. It's quite interesting. Now with Ito, emboldened by this kind of use of numbers, I went on to something very speculative. This was a design for the first time coming entirely out of numbers to make a building. This was for Selfridges in Glasgow. It's a design we almost pulled off. This was the time Selfridges were investing in radical designs. They hired, I think Birmingham was done, and there was another store. It was a very active period, I think mid-90s or late 90s. So this is a thing called Ulam's Rose, and it's a spiraling form that just goes round and round and round. And I just numbered it. I took the rows and just put numbers down, just kept going. Then I took a cut through them and made, that's the sample of the numbers, and I called it the second floor. You can see how arbitrary this is to begin with. Then I call it the third floor here. But then comes essential in playing with numbers and making things that is work is a kind of compression, a kind of coding. The fact we have laws in the universe the surprising thing is that we have laws at all. It's because data is compressed. And therefore, you can come up with something like E equals mc squared. It actually follows by compression. So I just took that idea simply and compressed the numbers. So if number, whatever this is, 16 becomes 7. 1 and 6, 7. So only single digits. That controls the spread of the number field. So then these disappear, and these become the floors. Then, wherever the floor was, say I'm at a number 6, I invented a very small vector that displaces, if you're 6, you go to the 6th point in this vector, moving up in space. When you get to the next floor, if that was deemed to be a 5, then you look up the vector to the next number and go up 5. So gradually, this gave me what I call dancing columns. So they were zigzagging, waving in the breeze, and that's the field condition. What keeps them within reasonable is that tight vector that just gets you deflecting in space. Now, when you connect the floor up, and you look on plan and just connect the points up, you get a kind of distorted grid. And that goes directly into structure very easily with steel members, metal deck slab, concrete on top, and you've got a normal slab. Underneath is a slightly eccentric connectivity. And so there is a render of one of the typical floors. And of course, we were surprised that Selfridges went along with us, because the first time I presented it, I thought I'd be kicked out of the room. It was something crazy in a way. You know, how the hell do you make a building out of numbers? I didn't go through the whole theory for them. I just showed them the models. And there's a model we built as well to see the kind of lean-to going on. And surprisingly, some came straight from that technique by chance. And here's a test, testing the angles to see what we thought. And then computer visualization of how we may walk across space within how did this work in an infrastructure. What kind of field condition were we walking in? And we all thought this was interesting. And we were going with this. So we had project managers appointed by Selfridges. We had costs and budgets done. We even worked with the shop fitters to say, how would you work with inclined columns? How would you sell? You're not getting a Cartesian block. What do you do? So we spiraled forms like this. And this was all tick, tick. To my utter surprise, it looked like it was going to happen. And here's a lovely thing. As you look down the zigzagging, that is, you look down the dancing columns from top to bottom, they closed up. They created a kind of code because that little vector controlled everything and reduced and compressed. So in the end, there was some hidden order working that I hadn't anticipated. And some of them went straight. These columns went straight. Now, when I put a facade on it, facade was quite rough, well, drastic in a way, sharp. And Ito and I thought, well, that's fine, but that's where the theory stops. We need to put something else into it. And then we cut holes through here for vitrines, and then just stretched it. And that did a marvelous thing. It started curving the forms. And then these would have been the vitrines. Another take on it was to come like this, and maybe put a screen over here as a vitrine. And as I said, we were ready to go. And then the top management, chairman, changed hands, and the new people coming in were more accounts-based. I think the visionary lead that Selfridges had that created all that departed. And they said, no, we're not going to spend money on a new store in Glasgow. We're going to go back and consolidate some of other properties. So the project died. But out of it came some good. This is, interestingly, the facade. And what I found, again, I stumbled onto this, didn't know it at the time, that if you take what I call a polyline, one of those dancing columns on the facade, like that, there were 4 fundamental lines that led to these panels, A, B, C, D. If I took those lines, what was happening was, and then upside down to them, or mirrored them as well. So they're there, then they're mirrored, then they're made upside down and mirrored again. Then what happened was I had 12 panels forming up to f dash. And this was the algorithm, like a pursuit curve. If you go from, fundamentally, there are only 4 lines, 1, 2, 3, and 4, forming, and then you invert, one becomes upside down, 2 upside down, etc. And you can go through this 12 bands of panel size by just following A, B, C, D, 1, 2, 3, 4, and you keep going here. There's one way around all this. And that was interesting, but that was it. Years later, I had the commission to do a bridge in Coimbra, just near the project I first showed with Cecil. And I used that in an ornamental sense for the balustrades of the bridge. And I had 4 uprights, twisted and turned, mirrored, deflected, and it led to this kind of balustrades on the bridge. And here, because that glass couldn't be doubly curved, I cut and triangulated them and used only blue, yellow, pink, and green. Four types of color and 4 types of balustrade. So there's 4 types made and then repeated, and you get 12 panels, just like that one. And so what it shows was even that curved facade would have been precast in 12 components only that would have made the whole of the Glasgow Selfridges by this technique. And so here's the bridge, and the turning point, the bridge sets aside and moves from right to left. And that comes about from me positioning one side extreme support on the left, and by the time you come mid-span, there's nothing, and then the support turns back onto the right side. The sort of strong set aside. And there you see the bridge being built. It's sort of strong sculptural qualities. On the left, the structure comes, turns out flat, comes back down on the right. At mid-span, there's nothing. That's where the bridge sets aside. It's a 200-meter span, launching into space before the colored glass came in. But you could see these lines, if you track them, there are only 4 original lines. The rest keep going upside down or mirroring. And then, interestingly enough, because one support's on one extreme side, when the sun comes down, that's lit and illuminated as a fascia almost. And the other side has disappeared. So you get this lovely feeling of a huge leap in space of that line going right across. And the balustrades follow the pedestrian or the cyclist right from the approach ramps and across the bridge. And that's not a computer render, that's the real picture. Everyone thought it's computer render, but I took it from a boat looking up at it. And as the sun starts to go down, the colored glass lights up, catches fire almost. This is low fusion glass, very low carbon content, and body tinted, no applique. So that also the strong sun in Portugal, I want a very light palette of colors that light up. And then as the sun really sets and darkness sets in, you get a braid of light from the colors and the bridge. And this kind of cascade of light then is all that's left. They wanted to floodlight the bridge, but I refused. I just wanted the lights to be what you see. So this idea of cascade, folding, all of that, comes startlingly into an abstraction also of numbers. This is one of the most simple cascades you can run, but it's very profound. Anywhere I cut this, I will get a definite ratio like 3 over 8, 8 over 5, 13 over 8. Yes, those Fibonacci numbers come back up. Wherever you cut, you get those numbers. And this is also an algebraic equation called x squared minus x plus 1. So here is an absolute evidence of algebra being made concrete in steps, and hence the cascade effect. There's no definiteness in this. But if you cut, it becomes definite. Otherwise, it's a overlap of partials all the way down. 1 over 1 plus 1 over 1 plus 1. Nothing's definite in this. It's a continuous fraction. So it's in between the continuum and the discrete. And I find numbers get me there. And that's why I find more and more intrigue in trying to trick out in one way what is the continuum, what is discrete. And of course, they merge into each other depending on the limit of what you're looking at. Now, using those numbers, which are the golden ratio numbers, I can have a golden cube or a rectangular form like that and extract, if say blue, yellow, and red, that's all there is. I can extract from it, this part comes out, and in that subdivides again. And this recursive action can go on anywhere, and everywhere the proportions are the same. The golden ratio is at work absolutely everywhere here. Now, if I take a packing, solid packing of the red, yellow, and blue tiles, and then run an algorithm, let's say a simple logarithmic spiral in 3D, wrapping round, and taking away the first big blocks, then smaller blocks and smaller blocks, I gradually get this kind of erosion going on. That actually is a fractal in physical terms. If I model that, the reds are the voids, and the blue is solid, and you see the voids coming through from low level, spiraling up, 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 and there's a model I made of it to test it. This was a project in the Emirates for a museum, a mosque, and a school. And the museum was for rare scripts. And also I took that because it also meant no light. They didn't have any light coming into the rooms. So I took this sort of interstitial organization. And if you look through, you see the erosion form and the spiraling from the ground going up through, and looking up into the eye of God, right up there, these cubic forms spiral up. And here is a render of just, say, the mosque space, where the red, yellow, and blue tiles are still left there to show you how they were derived. It's an erosion, but you get big forms, smaller forms, and they're all in proportion to each other, in an identical proportion of the golden. Different numbers, but same proportion. And what was really interesting is the kind of section you get through a building like that. Not just a box form that covers space and a boundary. It actually is interstitial, cut in mezzanines, stepping up in space, and then fracturing at the top to smaller and smaller spaces up here. Underlying all of this is a very simple building module. Blue, red, and yellow, coming from those three tiles. These can be seen as diaphragms, or you can take out the solid bits and leave the frame, the edges as frames. So it could be steel frames or solid walls. And it's what's called a reciprocal grid, each one bearing on the other. That cascading effect of the numbers cascading are coming through here. There's no definite one beam on two columns. It's self-supporting each other. It's a sort of collaboration going on. And it leads to spectacular forms. When you model that, I had these very strong forms come out. Almost brutalist, and I kept them pure with no fenestration. But if one wanted to cut fenestration, if you look closely, there are patterns in here of that subdivision or that compilation going on. You can cut windows to that. But one form bearing on the other. And of course, the advantage of the Middle East is open skies, hardly rains. And given the nature of the program in here, one could do this. And the big voids, in the rooms, any one room, because it was all pixelated, you could then make a ceiling subdivided into pixels. You could take away the sides of these cubes and only explore the diagonals with wires, and you get a tensegrity ceiling. You start to approach, in a modern way, the kind of Alhambra, beautiful tessellated ceilings. Something is happening here. And with a little bit of work, one could imagine this at different generations going up into space and coming back. And on the roof itself over the mosque, by playing that game with different angles to the cubes, diagonals or otherwise, I can get different light patterns shooting down onto the floor. And as you open, the open spaces could be left open or covered with courtyards, reflecting this reciprocal pattern of those red, yellow, blue beams. It's in here. And the windows are residuals, again, of the erosion form. And as you look at the building, the big goes up to the small and fractalizes at the top. Much like Gothic cathedrals or the Renaissance idea that the church will have no ridgeline, but open up to God, in no firm line against the sky. You just fracture it and open up. And something's happening like that here. Now, if I keep eroding this thing, just in the computer now, leaving aside tectonics, and keep going, and then take a section through it, what I get is that. So no subdivision has happened here. It's kept branching. Here's the trunk, first generation. Here's the second. Here's the third, and so on. And what's happened is it's been branching in space, fractalizing, like a tree does. A tree is a fractal. The leaf to the twig, to the branch, to the trunk, to the root. It's all the same thing. Just different scales being applied. And it's open. And of course, we're used to fractals like this, the famous Mandelbrot fractal. And it's a simple equation that feeds back on itself that provides this magic. Here's the trunk, here's the trunk, here are the main branches, little branches, and so on, and it keeps replicating. But you don't have to have this kind of, well, it's called chaos theory, but it looks chaotic. You could have an amazingly symmetrical fractal, made again out of simple numbers, like the last one. And this is our DNA molecule. As we look down our molecule, the twin spirals going around, and the protein bases all here. Whether that's fractal, I don't know, but I'm just putting it up there for comparison. Something between those two things. And surprisingly, our numbers, coming back to the theme of this talk, a material number, the numbers can be fractal. So you take this number, let's take 6. 6 is a classification. It's 6 things, 6 points around a circle, or it's an object that has 6 sides. So it's a classification. But equally, 6 can spread into a matrix. So if you add these numbers in any direction, you'll get 6 in a simple way. If you go here to the oldest paradigm of numbers, which is the Chinese magic square, well over 2,000 years old, these numbers all add up to 15. And 15 compressed, 1 and 5 becomes 6. And in number theory, or the manipulation of numbers, I found that I can make this kind of set of numbers and this equivalent to 6. So suddenly, 6 is not just a classification, it's a field condition. And any one of these numbers can be replicated further with the same kind of idea. So you can build up a field of numbers. And say they were 1 to 12, or 1 to 10. And if 10 was black, and 1 was white, and you kept doing this and feeding it back into each other several times, 10 times, say, you could get a graphic like that, which clearly you can see is a fractal. It keeps going down and down in its own scales. The 10s become black zones, the 1s become white zones, and everything in between is going on here. This is 1 generation, 2, 3, 4, 4 or 5 generations going on here of cascading down. And just simple grayscale rule. 1 is white, 10 is black. And you get things like this. Now, I became interested in a different way to sort out the numbers when I started really thinking of numbers, material, and how do I get energy into the numbers? How do I get some liveliness into things? Because geometry is static, and we know with static forms we make static things. I wanted to go in some dynamic equilibrium, something different. And so I've realized if you just take a curve, a wave function, a wave is energy, I could, by setting up an axis, just take a number. So this could be 8 up there, this could be 10, this could be 2. Simply discretize it, very basic. Just mark the curve with points. And if this was, say, an amplitude of 10, then if this was 8 and this was 2, the ordinate, going up is 8, going up is 2, but they're held by the amplitude 10, then 8 and 2 are complementary, only because I set 10 as their boundary, as their mother. But the real number along this axis is different. This is a different number here to that there. But if I used 8 and 2 when in whatever I'm doing, I know there are complementarities in it. So by doing that, then I can forget the wave and stretch it all out on a string. And then these are points. If I take away the string, they're actually points in space. And if I have several waves, and I discovered 4 waves of increasing energy, a simple one, doubling the energy, tripling the energy, quadrupling the energy. Just had an instinct that somehow 4 things, like our 4 bases in our DNA molecule, govern everything. All the genes, everything get made. But the trick that nature has done is that the 4 bases can talk to each other. They are complementary. Once they're in 2 pairs. And just that further breaking on the 4 bases gives us all the variety we've got from plants, animals to us. So I, just instinct really, no other reason, I found 4 waves, discretized them, and then reversed them to go the other way. So this is one set of 4. So they were my, let's say, my 4 bases. Then I reversed them in here, and then I found, to my astonishment, because of what I had done, they actually were already going this way and going up the other way. So suddenly I had a field condition of pure numbers, that the pattern of the numbers, if you looked at it, went one way, then they went the other way. But by doing that, they went this way and they went that way. And suddenly I realized that actually there was a number field here that was in shear. So that is, around this axis, there'll be mirror symmetry. This side, which is like that, is equal to that side as I turn it round the mirror. And I knew there was deep symmetry in here that had to matter, but I didn't know how. So then I thought, okay, let's just connect the points up. Let's take all the 2's, say, that are complementary to 8's, connect all the 2's up in the entire matrix of points, say 600 points in space, in a cubic framework. Join all the 2's up. Take the 8's, join all of them up, and put them together in complements. They complement each other. And to my surprise, I had no idea this was coming, these kind of objects emerged. Utterly beautiful, completely closed, and completely modular. So I could take this as a brick and keep compiling a wall. I could do what I want. I could, of course, blow this up to a huge size and make a structure out of it, or shrink it and becomes ornaments. So same thing with pattern and scale at work, but they were amazing. As I zoomed into that one, you could see what was going on. And this is not doctored. The only doctoring is the way, to those of you who work with digital, the problem always is how do you mesh an object? The line work is there, dimensionless, but then you've got to flesh it. And there's, I won't go into it, but there are various techniques. I chose one technique. A different technique would have given a slightly sharper confluence lines here. Something quite strong, like a, don't know what it is really. So all these forms are coming out. I was speechless looking at them. There's another one. And you get these open sides as well. And those were renders. These are rapid prototypes I did in the office. I've made 4 of them. And I started to make them into small sculpture. So I took, I think, this one, and about this size, and took it into rhodium. And so I'm making small sculpture of these things to see what they. I would ideally love to work with the resin and have color flowing through the resin that reflect the way it was made. But I've talked to many people in the world and no one can do it. So Maybe one day. What people can do is make it with rapid prototyping now, with metal. And I'm making a series of these objects, 4 of them. But there are many. And these are like jewelry almost, these little spiders. And these are all coming from just connecting complements up together. But then I thought, how do I grow something, really grow something in it? And then I thought, if I took a pixel or a voxel, a little volume in the computer, so not now just a dot, something that can actually keep adding and growing in a way, and devises a simple rule that when you're here, look at what's around you in your environment of numbers, give some characteristic to number. 5 is higher than 4, let's say simply. Take a choice and move. And when you get somewhere, look back to where you were, get some information, because you've depleted what there was in energy terms. I'm playing an energy game now. And then look forward and keep going. And then I grew these simple worm forms. This is growing from a center in every direction. This is growing more in 3 directions in a way. But if I stop the growth in those, just started growing in one way only, and then hit a branching rule, you could come to a point where I say, if the numbers are nearest to 10, go to it, and depending on what's just behind you, what you've left, you'll get trapped, and you keep branching. You can't grow any longer. So that was interesting. And you had these kind of branching forms. And this is the first time I'm showing this work in public. It'll be interesting, what do you think? But we were absolutely stunned in the studio at this kind of work coming out. I never thought I would get into biomimicry or anything like that. I thought I'd be doing architectural product. But I was so interested. Everyone who's worked on this wouldn't stop working on it. They got so interested. So we've kept going to see where will this go before I get some sense back into me and do some real work. So here's another branching product. Something strange again. And some beautiful things. Rapid prototype. And these could be, in fact, there's a sculpture in Chicago I'm trying to do with this. Imagine this on its side and about a 20-meter span in a park, and you walk underneath it. So that's what I'm trying to do on that one. So these are all going easier into art than into architecture, obviously. And these beautiful forms too. And then came this idea of the number as a fractal. So here is the primary growth. Here is the environment. But now I go to a point here and switch on all the refinements of this number. Like the 6 had a field condition, and within it another. Here switches on a whole microenvironment. So this is the main matrix it's running through. But I say stop here and switch on a whole micro. It's really, again, the way our genes work. They're all there, billions of them in the cell, but only a few switch on to grow the trunk, the arms, the head, then fingers, and then gradually the others, they stop and others switch on and start growing all our detail. And I mean, very crudely, I was trying to echo that idea. I mean, I keep searching for more, but it's hard. So this was the nearest I got to it, and I found I could grow then. So if I go back here, sorry. Here is the worm, say a line. The microclimate grows the same form, but in small ways. And so that's what's happened here. Here's the primary form, and then here's the spikiness. And here's another one where a cratering happens along the surface with the micro environment. Some kind of sea monster coming out, wrapping itself around like those early worms I showed you, but this time fleshed out more with tubulars, suckers coming on. And this is in a cubic environment, the data. But now then, progressing, I went to a Russian doll kind of spherical environment. What if the numbers are in a sphere? And the numbers are guided, so where there's a 4, you could switch on inside something of a 4 with all its environment in there, and you start to nestle one thing into another, sort of Russian dolls going, imploding inside. Then when you join up and do the same search paths, you get some amazing results. This is a very nasty looking virus. People don't like looking at this. Actually, I like it because it's so wild, so unpredictable. I didn't think anything like this would come. So zoom in, and then things like this, like our lungs almost. Look at that. So it would have started growing and then quickly branching out and then collapsing with the Russian doll effect going on. And I have to thank various people for the coding and the help here. One guy is Rob Stewart Smith of the AA in London, who's worked with me on and off for 5 years. These were done by Casey Rhyme in New York. So I've had people, when I teach at Penn at my school, I have students as well doing work for me. And this is a lovely thing, going back to the cubic environment, but growing and then switching on micro environments. Fractals open up. It's like things hanging in the sea and growing down, chain reactions happening. Rather beautiful tracery going down. And then forget all the geometries that prescribe the numbers. Just throw them into a pot, literally. So all the numbers have lost the cubic environments, spherical environments, throw them all in. And amazingly, because they have these complementarity rules, they start to make form. And surprise, surprise, along that axis, they start to form bilateral symmetry, like most animals have. And the time sequence shows no distinction at the beginning. As time runs, it starts to separate into form. If I particle that, you start to see again, this is I don't know how many seconds, 755 seconds, I think that's, I can't read that, 200 or something. More and more definition comes. So where this all goes, I don't know. We've got hundreds and hundreds of illustrations of this. This is just a sample. But I've decided to stop, no more, publish. Maybe people are advocating to do an app or some kind of game on the net that people can use this code and start to do things. And that's interesting too for me. So what we have here is the traditional starting point of the hand, the clay, the tools. What all this work on the research is, the materials turn into an environment. Products are now not definite, they're partials. They happen in time. This is an evolutionary process. And the tools are algorithms and assembly methods. And this really transforms into a higher abstraction of information to data. You may think data should be there, information here, but no. For me, information is environmental. Data is product. And it's no surprise the banks are paying fortunes. Some of my best computer scientists I had have left to join the banks and get paid highly to encrypt using prime numbers as information. And from that, they get data chains that give us our security on BlackBerries and bank transfers and all of that. And so, just to close, I want to show a couple of simple art projects that were taken from prime numbers, the way I look at them, not in any advanced way, but they're amazing numbers. And as you know, they cannot be divided. They have no factors. They are themselves. You can only divide 229 by 229. There's no other number that can divide it into a whole number. And no one has ever found the greatest brains, even Gauss, Friedrich Gauss, the greatest mathematician ever, could not find. He spent 30 years trying to find what connects these up. No one has found the secret. They're just there. It's amazing. And I love the fact that it's a permanent mystery in our midst of rational thought. It's totally irrational. We have no idea how it's made, but we use it all the time to encrypt data, to do things, and I use it simply graphically. So I went in here about 8 years ago, studied them, and found interesting trends. And so I found that every even number is made up of 2 primes. So 8 is made out of 5 and 3. And the higher up you go, like 38 or something, you'll have many sets of 2 primes that add up to make the 38. And as you go on, so 38 will be somewhere here probably. As you go on and on to 300, 400 as an even number, you'll have various couplets of primes adding up. So I just marked them out as ciphers, just dots or bars, you know. And it's this wonderful opening, and it shows the serial nature and the fact that this is something fundamental in our midst. You just know it when you look at that. And I was only plotting even numbers made out of primes. But it was wonderful. And if you zoom in, you get like a barcode. And so when I had a commission to design a light sculpture in Alaska, I'd never done anything like it before. And I thought, why not this? So I did a little sketch. And here's my sketch of the prime code and what would I put as lights, acrylic lights on aluminum rods or stainless steel, and came up with this. And these are spaced directly from my little template of primes. These are acrylic with LED lights, stainless steel bar, and stainless steel plates. It's only 9 meters high, about 2.7 wide, but there are two rings, one within the other. And because of the nature of this stepping serialization, you lose again all sense of how limited this space is. It feels much more open. And as you go in, I also found that these are acrylic, and some of them stack up. It all comes from the spacing. I could switch on computers controlling the LED lights, and they're sort of ghosted. They hang in this space through an interference pattern. Again, I hadn't anticipated that. 4 LEDs ran down, they interfered with each other in a cruciform, and they created this shadow, or this suspended light. But then, therefore, I could swell it and minimize it. And so these lights could fatten up, and the whole acrylic is there fat, or it thins out. And this growing and swelling and diminishing around in 2 circles gave a wonderful feeling. This is the 2 circles laid out. I could put, because it's computable, you could put speed into it. The lights could go ch-ch-ch-ch. You could put color. I decided in the end, talking to the owners of the building, it was a public art project, just to swell the line and minimize the line. And that alone would give the 3D effect I wanted. It's looking up, and the prime code goes around the glass and reflected in the glass and the mountains of Alaska over there. I call it snow words. The snow coming in, a sort of poetic idea for the light. And I'm happy to say this won a national award in America. So I was very pleased. I'd never done anything like it before. So emboldened by that, of course, step forward, go to another talk of the primes. And this is the primes moving around its gaps in a simple way. It just keeps moving. And because the primes are endless, if you follow this line, I don't know where I started, somewhere. This is a sample of a very big plot. And I go round and round and round. So I just took that and cut, water jet cut, aluminum. And this is for Edmonton, about a 30-meter stretch of wall on a university campus. I've spaced it about an inch away from the wall to get the shadow lines. It came in parts that were bolted on. Very cold winter when this was going up. And lovely Art Deco moments. And there's freezing weather. And the idea also was that the snow would get trapped like a lattice for a while, the heavy snows, creating a kind of interesting snowscape. And I took the pattern inside for warmth. There you go in. On the glass, all the officers and admin officers are here. It's the glass, a vinyl tracing, very cheap, stuck on the glass. And I used the colors of the spectrum to spread it down the corridor. The corridor is about 40 meters. So in all the work, as we organize, as we design, as we shape, there are templates we use, classical ones or contemporary ones. It's always some kind of principle of organization driving us between the material and the product. And in primitive sense, it's tools, but as we get more sophisticated, the tools themselves become processes that influence material and product. And when the numbers are the material, the in-between is swollen up to absorb it all. It blurs the distinctions. And that's a modern condition, that categories are being eroded. It's uncomfortable for those who want simple classification. But we have to face up to a complex world. It's not a difficult world, it's complex. It's not simplistic, it's not reductive. It's additive, it's compiled. That's the fundamental difference that I find and I believe in. And when the material is just us, we still have templates. I think this is Isadora Duncan. There's still principles of organization and containment and geometries. In this case, in dancing velocity. And we have classical, mystical organizations, and we have provocative ones. This is the orbit. And these are 2D cut through spheres on a cone, and a line whips around the spheres to form that orbit. And then copying directly from physics. This is a well-known thing discovered 20 years, 30 years ago, called the Lorentz attractor. It's a fabulous thing that goes round and round in space-time, containing all sorts of information. It was a great discovery when it was found. And I love this idea that it keeps reversing and going. And I cut this to a simple 2D version, what I call a single point attractor with our decimal system. And then I found this, got rid of the lines, got rid of the numbers, took the arcs here as compression, took the lines here that connect them all up in a way as tension. And I created a sculpture for an exhibition in Florence last year. It's about 2 meters, 1.5 meters wide, and they're compression arcs held together by tension wire. And if you see carefully, the middle, which holds all the wires, doesn't touch anything. It's balanced between the wires and the compression. And I call it equilibrium for obvious reasons. And there's a close-up showing the kind of energy going through it. And that pivot point doesn't touch anything. And it all began so long ago with a wire being stretched. This was the first scientific experiment ever done by Pythagoras, 2,500 years ago. And he found if you stretch the string, anyone who plays guitar will know this, stop it halfway, you get the octave. So half gives you the octave. If you stop it at the 2/3 point, you get the dominant chord. And if you do it at the 3/4 point, you get the subdominant. And octave, dominant, subdominant is the basic harmony structure of all our Western music. All pop music revolves around those three, basically. Even Beethoven's Ninth, the opening chords, go around the 3 chords. And so Pythagoras was elated. And then he found that these numbers 1, 2, 2, 3, 3, 4 can just become this. 4 elements, 3 for spirit, duality, unity. And they add up to 10. And 10, 1 and 0, made unity again. So they took this, they called it the Decad, and they called this their secret emblem. Secret Brotherhood could not give this out. This was their treasured emblem. And they thought, therefore, the world and God made the world divine through numbers. And from that, 2,500 years ago, has come this fascination through Plato, through Augustine's City of God. They were all made by numbers. All influenced by this one experiment, because music was made with whole numbers, and it was unbelievable, of the Decad. So no wonder it came to hold such a fascination on people. And the idea of number and then geometry being made up, compiled, templates, organization, they all come back to the first intellectual language, universal intellectual language we've always had, which are numbers. It's the only language we can all talk in, across race and geography. And to my surprise, 2,500 years later, modern physics comes up with this diagram. So it's called a baryon decouplet. And under all our what we thought was solid matter, protons, neutrons, solid entities are now undermined by a series of partials called quarks. It's like our continued fraction. These slide in and out. The quarks have a down property, an up property, a spin property. And this is beyond me. I don't know how this all works, but this is a template of modern physics which serious particle scientists use to classify all their quarks. And I think it's wonderful that they've come out with another decade. They call it the Baryon decouplet. And they're all partials, 3 over 2, 1.5, 3 over 2, suspiciously near Pythagoras' stuff. And, you know, who knows? It's strange, isn't it, that all the partials. So our reality, what we think is definite, our definiteness, is undermined by a series of partials moving in and out of existence. Fluid number. The man on the left here would not have been amused by this. He believed that God did not play dice with the universe. Everything was known, definite. And he did define a lot of it, so one has to give it to the guy. The man on the right, I think, he didn't know about all these quarks and things. I think he would have had a laugh at my numbers as well. Thank you very much.